And we are now ready to dive into our next topic for today, advanced material for electronic. And it's my pleasure to introduce Dr. Eric Kwok, Senior Technical Manager at the Nano and Advanced Material Institute, presenting on advanced thermal management material for 5G connection. We're definitely excited to learn more about the latest innovation enabling next generation connectivity. Let's all welcome Dr. Kwok, and the stage is yours.
Okay, thank you so much for the invitations and the kind introductions for the presentations. So I'm Eric, coming from NAMI, the research institute in Hong Kong. So today I'm going to share critical issues about some of the advanced thermal management materials, especially for 5Gs or even in the power electronics. So as you know that every day we will get in touch in different kinds of electronics. So we are asking for different kinds of applications. We are looking for different kinds of the useful aspects for the electronics materials. So the power densities of the electronics material is become higher and higher. So how to resolve the heat generated by the chips or from the PCB is a critical issue that need to be resolved. So one of the critical materials is called TIM materials right here. So it is mainly used in between the heat source and the heat sink right here. So the major applications of these TIM materials is to remove the air gap between the interface. As you know that the interface joint may not be very perfect. Some of the air gaps in between the contacts may have a very high thermal resistance. So what we are going to do is to develop a new methods of TIM materials that to resolve the heat transfer properties. So we have developed different kinds of the thermal management materials, starting from the motherboards, as we have said, the TIM materials. So we have developed different kinds of thermal packs and some kind of thermal gel to interface the connection between the heat source and the heat sink. Besides that, we are also developing some kinds of nano materials that for the chips bonding to the PCB. Some kinds of nano materials such as the nano silvers or nano coppers materials to bond the to provide a very effective heat transfer properties. So besides some of the packaging designs, we are also focusing on some of the system type thermal management materials. For now on, we are working on some of the high-end cooling system, which called the immersion cooling. We are targeting to immerse different kinds of the electronic boards or electronic system into the liquid that we have made or designed for this kind of applications. So we are talking about different kinds of thermal management materials. Of course, we are open for different kinds of collaboration with the industrial parties. So here shows some of the successful case that we have developed during the past few years. Besides the research and development work, we are also keen on getting different kinds of the international awards, such as the Geneva Awards and some of the awards given by the U.S. government, U.S. institutes, such as the RD 100 Awards and the Edison Awards. So these kind of materials are mainly used for the resolving the thermal management materials. So where they can be applied in the system. So one of the biggest market is the consumer electronics. As you know that you got the cell phone in hand, you are asking for different kinds of the applications. Thermal management is a very critical part for this. So besides that, one of the challenging parts is for the thermal management is the batteries. So we have different kinds of the vehicles that are asking for a high battery system. So how to do a better thermal management on the batteries is very critical. And other kinds of applications such as the 5G base stations and some biomedical device, and also asking for some of the thermal management directions. So what we are doing is developing different kinds of the thermal management materials. So our technical breakthroughs on the thermal management is slightly different from the conventional materials in the market. So for the conventional materials, they are mainly use some ceramic types of the materials to be the heat conducting elements. So this kind of materials is most likely will be a spherical particles. They will get in close contact together, and then they provide the heat transfer by a kinds of a skin contact. So the heat transfer may not be a very effective way. So what we are doing is to make use of some of the advanced materials. We are trying to align these kind of materials in a single directions. Such that the heat transfer will be very effective, because the heat transfer is mainly from the heat source to the heat dissipation area that you are going to. So what kind of materials that we can choose for this type of the anisotropic heat transfer properties? We are using carbon-based materials to be our heat transfer materials. So as you know, that carbons may have different forms in terms of the natures of the materials. For example, it can be kinds of carbon fibers. We use a lot of graphite materials to be the heat conducting materials. Besides that, they may also have some kinds of, you may get in touch a lot with the diamonds powders. And as they are all kinds of this kind of carbon-based materials, can be a very effective heat transfer materials. So regarding materials, how to make it align is a critical issue or critical challenge that we need to be take care of. So because of the materials may have different kinds of the properties, we will use different kinds of the alignment technologies to further align the materials. So as you can see here, and we are using kinds of electrostatic flocking technologies to align the carbon fibers into a polymer substrate to enhance to ensure the materials are all well aligned in a single direction, so that the heat source and the heat sink are all aligned in the same way. So for the graphite types of the materials, we use another kinds of the magnetic induction techniques to align the materials, which means that some of the nanoparticles are adhered on the graphite surface, and once the magnetic powers are given to these kinds of materials, it will align automatically. So for the spherical types of the materials, we are trying to also doing these kinds of alignment, but just based on their size principles, which mean that different kinds of the size materials to have a very close packed structures to enhance the heat transfer properties. Here show one of the successful case about the developments of the carbon fiber-based and isotropic thermal management materials. So you see here these kinds of materials, it have a relatively high thermal conductivities. So we are also trying to get some of the related materials in the market to do some benchmark comparisons. So based on our electroflocking technologies, we should be able to align the carbon fiber in this very unique directions, so that the heat transfer properties can also be improved a lot. As you can see here, the thermal conductivity can be boosted up to about 30 watts per meter kelvins. So instead of the highly thermal conductive, it also have some kinds of softness to enhance the good contacts between these two interfaces, such that the thermal resistance of the materials will also be lower. The heat transfer properties can also be improved. So another types of the thermal management materials will be the graphite pad. So similar case with the previous applications, we are also trying to get a breakthrough in terms of the thermal conductivities. Besides that, because graphite may also have a kinds of the wave absorbing properties, so we are trying to make use of this kind of features to combine it with the heat transfer properties, such that the materials can have a kinds of dual function. It can also transfer the heat, and it also be able to have certain kinds of the EM wave attenuations. So another kinds of the thermal management material is the thermal gel. So thermal gel is kinds of materials that also bond between the heat source and the heat sink, but for this time, they are requiring a very low bond line thickness, which means that the thermal resistance of the materials will be pretty much lower than that of the thermal pack. And besides that, because of the gel natures of the materials, we are also asking for a very high dispersion rate because it needs to be fulfilled some of kinds of the automation dispensing properties to ensure it can be incorporated into the manufacturing facility easily. So going to the system, recently we are working on another kinds of the advanced immersion cooling. So why we need to develop the immersion cooling? Because of the launch of the 5G or AI applications. So conventional air cooling may not be cooked with the high energy density breakthrough in terms of the CPU or even in the GPU powers. So by using this kind of immersion cooling, we can further reduce the size of the cooling system because we no longer need some air cooling system or AC system to cool the surface. Besides that, many papers also report that the power usage efficiency of the system can also be improved by using this kind of immersion cooling. As I have said before, we are trying to immerse different kinds of the electronic component into this kind of liquid. So the liquid may need to have different kinds of the properties that need to be fulfilled. Of course, the first of all, I would like should be the safety because you won't let the electronic components to be burned or even your liquid to be burned together. So the liquid need to have no flash point, and also the liquid need to have certain kinds of dielectric performance. And because it needs to be thermoconductive, so we are also targeting on different kinds of the thermophysical properties improvement. For example, the thermoconductivity, which means that the heat transfer from the electronics component to the liquid. And because of the theory for the heat transfer properties, we are also looking for the materials with a very high specific heat or even the heat of vaporizations. Okay, so a very complicated tables, but just briefly give you an idea that for a liquid that we need to be considered that may have different kinds of the parameters that we need to take care of. So in terms of the heat transfer, we are targeting to develop the materials with a very high specific heat, latent heat, or the heat of vaporizations. And besides the thermal properties, we are also looking for some materials with a very low GWP and OTP values because the materials also need to be sustainable to the environment. So how to validate our liquid developed? We have developed a kind of the immersion cooling system right here. It's a kind of a small system at this moment. We are trying to scale it up into a server-grade immersion system in the upcoming months. So in this system, we have developed a kind of the cage to locate all the liquid into the system. And in the system, there will be a kind of the motherboard and also one of the GPU system co-immersed into the liquids. So once the system operates, the liquid will have different kinds of the heat transfer pathway. As you can see here, this is the heat generated by the GPU system, and the heat from the GPU chipset will be directly transferred to the liquid. So this kind of liquid is not water. It's the kinds of engineering materials that we have made to fulfill this kind of the specific kinds of the heat transfer performance. So we have used some commercially available software to benchmark the performance of our immersion cooling system. So from our test result, in some cases, we found out that the heat transfer properties for our immersion cooling system is better than the conventional air cooling. So we are trying to immerse different kinds of the electronic component into this kind of liquid. So the material compatibilities and also the toxicity of the materials will also be very critical. So we have conducted different kinds of the material compatibility testing. For example, we are trying to put this kind of plastic, rubbers, or even the metals into our liquid to accelerate the aging of the material to see what kind of components will be decomposed or even corrode by our materials. And we also have a very long-term reliability testing to ensure the materials will have at least 5 years stabilities during the operations. And also, one of the critical parts will these chemicals toxic to the environment or even toxic to humans. We have conducted different levels of the toxicology testing. For example, the acute toxicity in terms of the oral, dermal, inhalations, or even the irritations to different to the eyes or even to the skin. They are, most of them are not classified as the kinds of irritants. So we have conducted different levels of the research. Actually, we have a lot of thermal-related characterization techniques in our laboratories. So we have certain kinds of the instrument to help us to do different level of research. For example, the thermal pack or thermal gels, we need to measure the thermal conductivities or even the thermal resistance of the materials. And we also have different kinds of the instrument to measure the thermal physical properties of the liquids, as we mentioned, the coolants. So we are coming from NAMIS. Actually, it's incorporated in 2006. It's kind of Hong Kong government research institutes. So we have different research talents in NAMIS, and we also have many different kinds of equipments in Hong Kong Science Park. Yeah. We have besides that, we also help our customer to file patents for the technologies or inventions. So as mentioned, we are located in Hong Kong Science Park, and then for NAMI, we have 6 different kinds of the sectors. So today I'm coming from the electronic sectors, and we also have some of the research based on the healthcare, environmentals, energies, or even in terms of the batteries, and also for the construction materials. So we are doing research actually, but we are also targeting for commercialize our research to the products level. Actually, we are open up for further collaboration with the industrial party to develop new materials in the futures. So this is the end for my presentation. Thank you.